Hello and welcome back. We're to our fourth day of geometry, so we're going to talk about special angles today. Typically, today is when I would teach you guys how to use a protractor, but because you guys don't have protractors at home, we'll have to do some of that protractor and compass work whenever we come back to school. So all of the protractors will already be printed onto the homework assignments, so we just had a few changes. Let's start out first. By the way, you guys are doing really well in doing the homework assignments, asking for help, and I can push those solutions out to you. And I think that's helping you guys think through the problems a lot. So you guys are doing well. Let me show you a few problems like the ones we had yesterday that were causing a few issues. So back to the segment addition postulate. Segment addition postulate says that when we have three collinear points, and say C, for instance, is between the two endpoints A and B, then segment AC plus segment CB is going to be equal to the length of the entire segment, which is AB in this case. So if we are told that AC is given, the length of AC is given by the expression 4x minus 5, and CD is given by the expression 3x plus 12, and AB, the distance between A and B, is 49, which is the whole thing here, then we can set up an equation using the segment addition postulate. In this case, that would be 4x minus 5 plus 3x plus 12 is all going to add up to the whole thing, which they said was 49. I'm not going to go ahead and solve the problem, but from there we would combine our like terms, right? So 7x plus 7 is equal to 49, and we subtract 7 from both sides, divide by 7, and we'd end up with x is equal to 6. Well, I said I wasn't going to solve it, but that's how you do it. All right, this one is a little different because notice they don't tell us what df is equal to, but we can still solve this problem. Do you notice something about this diagram that's different from the last one? All right, on this one, it tells us we have these little tick marks. These are congruency marks, and they tell us that those two segments are exactly the same length and that those segments are congruent to each other. Now, even though E does not look like the midpoint, right? That would be what would look like the midpoint, right? Even though it looks off, if it tells us they're congruent, that means they're congruent. It just means it's not to scale, okay? So going from that, what do we know if this is the midpoint? If those two sides are congruent, that means their measurements are equal. So we can set the expressions equal to each other. We don't know what they add up to, but we do know that they're equal to each other. And from there, we can solve by subtracting x from both sides, adding 2 to the other side, and we'll end up with 2x is equal to 6. Divide both sides by 2, and we end up with x is equal to 3. You know, algebra, that stuff. All right, so let's talk about angles. Angles are formed when we have two rays that share a common endpoint. When those two rays go in an opposite direction, they're called opposite rays, and it's a straight angle, which is 180 degrees. But any other time, it's still going to be an angle. So in this case, we have two rays with common endpoint. We have ray AB and ray AC. They're not going in opposite directions, so it's not an opposite rays, but they do form an angle. The vertex of the angle is going to be where those is going to be their common endpoint. So we call that the vertex. That's the point A right here. And then we measure the angle from the smallest side here, and we want to know what is the measurement. That was weird. Okay, so what is the measurement of angle CAB? So what we have to know how to do is how do we annotate angles, and I think I've shown this to you before, but we always put the vertex in the middle, and we start with one of the endpoints, or one of the points that the rays go through, so CAB. You could also call it angle BAC. So either way, works just fine. So whenever we're measuring angles, we measure them out of 360 degrees, which is the full circle. But where did 360 degrees come from? So you might be thinking 360, that sounds really similar to how many days are in a year, right? Like 365. And that is close, and that's actually kind of cool. They actually use that for the calendar to estimate the number of days in a year. They used to just do 360, and then they would correct for a few days that they were off so that the seasons would line up. Okay, so that's not a bad estimate, but it actually comes from the Babylonians, from the Mesopotamian Empire. I think Babylon, which is modern day Baghdad, so in Iraq. So, and Babylonians about 1800 BC, they came up with a sexagesimal system. And they would count, like we count to tens, they counted to 60s. And from that, 60 times 6 would give you 360 degrees. And so that's kind of how it came up, and I'll show you that in the next slides. But then after the base 60 system, we went to Roman numerals, which is from the expanding Roman Empire. And in Western geometry, I mean, all of Euclid and stuff was using Roman numerals to do their numbers, which would have been really, really difficult. If you're familiar with Latin, you probably know Roman numerals or think the Super Bowl or something like that. But then the Hindu Arabic decimal system that we use now that actually has place value in 0, which actually had a value in itself, was developed around 500 to 600 AD. And then Brahmagupta, who was a famous Indian mathematician around 1100 AD, he wrote a lot on the decimal system and the number system. And Leonard of Pisa, who is also known as Fibonacci, like think Fibonacci sequence, he was a merchant who traveled to India, saw their superior way of doing math with the number system that we use, the Hindu-Arabic number system, and he brought it back to Europe, and it spread through his writings. And from port to port, he showed people how they can use the decimal system like we have, the Hindu-Arabic system, which is what we use to this day. But before that, the very first counting system that people used back in the Babylonians was base 60. So what's the difference between a base 60 sexagesimal system and the decimal system we use here? So the reason we count to 10, you would think, or the reason the Indians were counting to 10, and the Egyptians counted to 10 as well, they just didn't have it developed with the place value like we got from the Indians. So that is because we have 10 digits, right? So you can count 1, 2, 3, 4, just like you would think over here, right? Well, the Babylonians, they would count the spaces in their fingers, and they would use their thumb to mark them off. So their thumb was like their counter. So they do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then in their other hand, they would mark it off as that was 1/12. And they would start at 1, 2, 3, 4, 5, 6, etc. And then 2 12s, and they would start over and over again. And that's how they would count. And by the time they got up to 5 12s, and they used all 5 of their fingers to get up to 12, that was 60. And so that's how they would count up to 60. And so in the sexagesimal system, kind of like our decimal system, by the way, with the Hindu-Arabic, with Brahmagupta and stuff, they had a decimal place. But back then with the Babylonians, they didn't have a decimal for place value. So they would infer the value based on its context, which is kind of cool. But not nearly as good as what we have now. So the first position in the decimal system is the ones. So this 10 to the 0th power, which is ones, okay? So that would be just 3. And then over here we have 10 to the first power, which is the tens position. So this would be 23. And then here we have 10 to the second power, which is the 100th position. So that would be 123. Of course, you know how to read this. This is what we use natively. And then the decimal after that, now it's to the -1 power, which is really the inverse. So it's 1/10 or a tenth. So that would be 4/10. And then to the second power would be the 100th. So that would be 45th or 45 hundredths. So over here in the sexagesimal, because they were doing base 60 instead, the first one is going from the first place value would go from anywhere from 0 all the way up to 60. And once you got to 60, you'd now be counting with 60s. So 2 60s would be 120. So this would be 100. The 23 we would read, they would read it as 2 60s, which is 120, and then 3 1s, so 123. That's ironic. That's what this is. But the 1 here would be the 3,600. It's going to be 60 squared. So 60 times 60, which is 3,600. So this number, 1, 2, 3, would be read 3,723. Crazy, but for us just to read 123.4 and 45 hundredths, to them, they would be able to read that pretty quick because that's all they've ever known. So about sexagesimal, I know it's kind of crazy stuff, but I think it's interesting with the history. And you guys are in honors, so you're going to get some really cool stuff like this and more to come. Think about minutes. We do 60 minutes and 60 seconds, right? So that is actually kind of a throwback all the way to the sexagesimal system from the Babylonian Empire in 1200 or 1800 BC. We still use that system because it works really well for time. Same thing with 360 degrees that we use in a circle, right? And then the same thing with hours as well. So 24 hours in a day. That 24, and then we break it down into 2 12s, right? And the 12 is actually a multiple or a factor of 360, and I'll show that in the next slide. So where did the 360 degrees come from? Well, the Babylonian mathematicians were very familiar with an equilateral triangle, which all of these sides were 60, and they had let those be 60 degrees because, again, they counted everything in 60s. And notice that there are 6 equilateral triangles that fill up the regular hexagon, which goes all the way around in a circle, which makes it easy to construct a circle as well. So they would do, that's where they came up with 6 times 60, which gave them 360 degrees for a full circle. So that was really natural for them. So I want to show you guys a short video that I show every year. It's really funny. So go ahead and watch that, and then I'll come back.
That don't even make any sense.
Why doesn't it?
Well, tell me how that makes any sense.
I've got a spider on my foot.
Tell me how that makes any sense.
Because what about the 30 degrees thing?
How does it make sense?
How does it not make any sense?
You're saying it's not been that hot. It has been hot, clearly.
Yeah, obviously, because I'm sweating, but it's not hot on the degrees circle.
What are you on about, the degree circle?
The 360 degree circle.
Yeah.
Yeah, it's not that hot, is it? Because the 360 degrees is there, and then
What are you going on about?
the 30 is like here.
What are you going on
Right
about?
there. Right, so this is a 360 degree circle, Brad,
Of what?
of hotness. Yeah?
Yeah.
So 30 degrees is going to be like there maybe. Yeah?
Yeah.
So all of this hotness
Yeah.
is left to get us. So
What are you going on about?
like there's still that much hotness left.
What?
Do you get that or not?
What? So the 300 degrees there, 360 degrees there. Yeah. The circle of you say hotness.
Minus 30.
is
which
330.
No, it isn't. It's 350.
360 degrees minus 30 is 330.
380 in it.
No, 360.
300, whatever. 360 take away 30, right? So that's 360. What's half of 360?
180.
So that's that, yeah, then in it, straight down the middle. So
Yeah.
that's half hotness there, right? And then
What are you going on?
What's half of 180 degrees?
90.
So that's obviously there then.
Yeah.
So we've got that half, we've got full hotness, half hotness,
Quarter hotness.
quarter hotness, and then 30 degrees there. So we're here on this hotness, yeah, out of the circle. So could you imagine what it's going to be like if it ever got to 360 degrees? Because I stink right now, and I'll dread to think what I'd smell like right there.
Look, let me get this straight. You think 360 degrees
Yeah.
is the hotness?
Yes. And 30 of that is here, which is what we've had today. Do you don't understand what I'm saying, do you?
Do you understand what you're saying?
Well, obviously, because I've just explained it with the circle. So you don't understand me, do you?
How do you understand do you get what you're saying here?
Obviously, I wouldn't have just been explaining
So
it
what's
like
the
that.
360 degrees in like science lessons then?
What do you mean? I don't know. I'm just going on the 360 degrees of my circle of hotness, yeah?
All right, welcome back. So I hope you enjoyed that. That was like 2 seconds for me because I just paused and inserted the clip, but that's okay. All right, so factors of 10 and factors of 60. So why was factors of 60 chosen instead of a base 10? Well, the problem we have when we have base 10 is there's only 4 factors of 10, which are things that you can multiply in order to get to 10 evenly. 1, 2, 5, and 10. So what happens if we try dividing by anything that's not a factor of 10, we end up with repeating decimals. Like when we do 10 divided by 3, we get 3.3 repeating, which is kind of annoying, 3 1/3, right? But when we have factors of 60, you have factors of 1, 2, 3, 4, 5, and 6, which is really nice. And it's the smallest number that has all of the first 6 numbers are factors of it. So that means we could divide by any one of these numbers and the other ones from the other side, and it would divide in evenly, which means 60 and 360 are really easy numbers to work with when you're dividing. And so their mathematics in the Babylonian Empire advanced further than the Romans did because their numbers were easier to work with because they were easily divisible. So even though sexagesimal sounds crazy to us, it was actually fairly easy to work with, even though I'm glad we don't work with it still to this day. The Hindu-Arabic number system that the whole world uses now is far superior, because of place value mainly. Okay, so if we divide it by 60 divided by 3, it goes in evenly into 20. And if we divide it by 5 or divide it by 6 or 12, it works out really easy as well. All right, so where did the whole clock come from? Well, if we go back to our 360 degree circle here, and I take this, I don't think you're ready for this. Check it out. That was fun. All right, so if we kind of double that up or split the bisect the angles for those equilateral triangles, now it breaks it up, instead of 6s, it breaks it up into 12s. And so they were able to make 12 hours, essentially 12 hours in a day. They knew this is actually how they did 12 first, because when they were doing calendars, they knew that there were 12 moon cycles, or 12 months is what we would call, in a year, going from winter to winter. So they knew that they wanted to break down the the year into 12ths, right? So if they broke down the year into 12 months, then they thought, okay, well, let's break down the day into 12 hours. And so they did 12 hours AM and 12 hours PM. And then from there, well, once we had that, they decided they would do minutes in 60 minutes, right? So that would be where each one of these would be worth 5, right? And so the whole idea of keeping time and the way that we have it all goes all the way back to the Babylonian way of breaking things down into 60s. And it's still used kind of in astronomy today with all the degrees that we use with 360 degrees. All right, cool. So now we are going to classify angles. So it's kind of fun history. I hope you enjoy that. Classifying angles. So acute, right, obtuse, and straight. You should know all this from middle school, but we'll go over it again. So here we have an acute angle. If we notice on this one, it's going to be less than 90 degrees, also known as coordinates. Yes, that just happened. You thought I didn't watch the video. Of course I watched the video. Then we have a right angle, which is also known as, of course, coordinates. Yes, yeah. You guys are getting good at that. Obtuse angles, which are less than afoutness, but more than coordinates. Yeah, it's fun. And then straight angle, which is afoutness. Yes, very good. Very nice. The Cockney accent. Okay, next thing we'll have is complementary angles. This is a special angle. Complementary angles are two angles that add up to 90 degrees. Before we look at complementary angles, we need to know what perpendicular means, though. So perpendicular are two lines that intersect, forming a right angle. Well, if the whole thing is a straight angle, which is afoutness or 180 degrees, then this part here would be ooutness. Yes, very nice. So what's left over here? Well, if this part over here has to be 90 degrees, the whole thing is 180. It means that these two angles add up to be 90 degrees as well. And we would call these two angles complementary angles. How do we keep complementary separate from supplementary? Well, if you drop a line from here, from the C, that's now 90 degrees. See it? 90 degrees, complementary. So that's one way you can remember. So anytime we have two angles that add up to 90 degrees, we call them complementary angles. An example of that, so again, the whole thing's 180 because it's afoutness. Coordinates over here, so the other half has to be coordinates as well. So what is the complement of 40? So the complement is just the part that's left over from 90. So if we take 90 and we subtract 40 from it, what are we left with? 50. So the complement of 40 is 50, and the complement of 50 is 40. So just kind of way that we use our vocab. The next one we have is supplementary angles. Now, as you can see here, supplementary angles add up to 180 degrees. We can remember that by taking the S, crossing it so it's an 8, putting a 1 over it, and then a 0 on the bottom. So you can see 180 degrees. Okay, so supplementary angles. So if we have a straight line here from the opposite rays BC and BA that are all collinear, and then we have ray BD that goes off to the side, and we know that this angle here is 50 degrees, what is the supplement of 50 degrees? So what we do is do 180 degrees. We subtract 50 from that. That's supposed to be a 5. You get it, whatever. Well, I can fix it. So I got 180 degrees, subtract 50 degrees from that, which will leave us with 130 degrees. So the supplement of 50 is going to be 130. There we go. One more thing that I do want to point out with supplementary angles is that we still would consider two angles to be supplementary even if they weren't touching. I know, it was there the whole time, so trippy. So these two angles are still supplementary because they add up to 180 degrees. But whenever they are touching, we have another name for them. By the way, whenever we have two angles that share a common side, we call them adjacent angles. So adjacent just means right next to. Okay, so you live adjacent to your neighbors because they're right next door, right? Or like if you share a back wall or a back fence with someone, then you can say that you're adjacent to them and they would be your neighbors, of course. So if we have angles that are supplementary, meaning they add up to 180, and they're also adjacent, we have a special name for those angles and we call them a linear pair. A linear pair is a pair of angles that form a line. So if you see, if we take this angle plus this angle, it will give us a straight line because it adds up to 180 degrees. So whenever they're not adjacent, they're only supplementary. But when they are adjacent and they are touching, then we call them a linear pair. You could also just call them supplementary, but this is just another term you need to know. What does it mean if we have a linear pair? On the assessments that we take, there'll always be a question that asks, it'll tell you that Angles 1 and angles 2 are a linear pair, and they give you the measurement of one of the angles is 50, and you have to know how to find the other. Well, you need to know a linear pair is a supplement, so the supplement of 50 would be 130, and the supplement of 130 is going to be 50. All right, next we have vertical angles. So vertical angles are opposite angles that are formed by the intersection of two lines. So for instance, if angle 1 is 50 degrees, we know that the vertical angle over here, 3, which is on the opposite side of the intersection of those two lines, the blue line and the red line, or line 1 and line 2. By the way, this is just a cursive or a script L. Often they use that to refer to a line, and then we are doing subscript 1 and L subscript 2, which stands for line 1 and line 2. It's just a way of labeling them. You might see that fairly often. So vertical angles, we are told, are congruent to each other. So angle 1 is going to be congruent to, I guess I should fix that. It's going to be congruent to angle 3. Now the proof for that is actually kind of cool using the transitive property, and it flows kind of nice, I think. So if angle 1 is 50 degrees and it's a linear pair with angle 2, it means they're supplementary, right? They form the straight angle or the straight line, which is going to be line 2. So what's the supplement of 50? Well, we know that's going to be 130, right? And then now look at the red line. We know 2 and 3 are a linear pair as well. So what is the supplement of 130? Well, the supplement of 130 we already said was 50. So it's going to be the exact same supplement on this side as well. And this is just a very simple proof for why vertical angles are always going to be congruent to each other. So let's apply this again. If these two angles are a linear pair and the supplement of 50 is 130, then what's the supplement of 50 going to be down here? Because again, it's forming the same linear pair. Well, this side would have to be congruent. All right, so let's go just a quick review of the new words we learned with our special angles. Complementary means that it's going to add up to 90 degrees. And we can remember that because we can always change this to 90. So complementary over here, if this is 90 degrees on this side, all right, so if this is 90 degrees over here, it means that these two angles also have to be a right angle, which means they're also going to be 90 degrees as well. Supplementary means that it's going to add up to 180 degrees, which is going to be a linear pair. So on this side, we can see that angles 2, 3, and 4 are going to be supplementary, or 2 and 6 are supplementary, or 3, 4, and 5, or 5 and 6, anything you want to do, right? So anything that's going to form a straight line, it's going to be supplementary, or simply if they add up to 180 degrees. Adjacent angles are angles that are going to be next to each other. So 1 and 7 are adjacent, 2 and 3 are adjacent, but 4 and 2 are not adjacent because they are not sharing a common ray. Linear pair are going to be a pair of angles that add up to 90 or 180 degrees, form a line. So in this case, that would be 2 and 6 or 5 and 6. So those are the only linear pairs that we have on the page. Vertical angles are going to be angles that are opposite of each other, and they're also going to be congruent, so formed by the same two lines. So in this case, is 4 going to be a vertical angle with 6? No, because they're not formed by the same two lines. 6 is formed by this line and this line here. So if I added 3 and 4 together, that would be vertical with 6, okay? 2 is going to be vertical with 5, right? Because they're formed by those same two angles, or same two lines, and the opposites are going to be congruent. 7 is not vertical with 90, because the one that would actually be vertical with that would be if we extended this line here, and then 7 would be vertical with that line, of course, if it was straight. All right, so let's get right into the homework. So the lecture went a little bit long. Sorry about that, but I showed you kind of the history stuff. I hope you enjoyed that. More to come on that kind of stuff too in this class. So on number 1, we want to find the measurement of angle MLN. So normally I'd have to show you guys how to set up a protractor where you center the dot in the protractor on the vertex of the angle, and then you line up the 0 line here with your horizontal line that you're measuring, the one of the sides of the angle, and we want to measure angle MLN. So starting at M, L is going to be our vertex, and then N is our third point, okay? So that's going to be the green angle right here. We want to measure that. So we're going to start at 0 degrees, and then we're going to go up 10, 20, 30, 40, 50, 60. So that is going to be a measurement of 60 degrees. All right, so this angle here, the green one, is 60 degrees. Now we want to find the measurement of angle NLP. So starting at N, then going to L, and then P. So that's going to be the blue one right here. Well, in order to find the blue one, It's a little bit difficult because we're going from 60. We start at 60 now, right? And then we're going on past 60 all the way to 130. So you could count. So that would be 10, 20, 30, 40, 50, 60, 70 degrees. Okay, and that is correct. Another way you can look at it is by subtraction. So if we know it goes all the way up to 130, okay, which is the red angle from all the way from this side, and then we're going to subtract the 60 that we started out at, and so 130 minus 60 is going to give us 70 degrees. Okay, so many ways that we can do that. Hopefully you followed what we did there. Usually if we have an actual live protractor, I guess I can show that to you. So if we have a live protractor here, what we can do, so I'm going to center it at the hole centered at the vertex, is what I would do is I would just rotate the angle to zero it out at 60. See that? And then all I have to do, I wonder if it'll, anyway, all I have to do is go from here 10, 20, 30, 40, 50, 60, 70, and I can measure out 70 degrees that way, okay? But whenever the protractor is stationary there, you might have to use subtraction, use a little bit of a trick there. All right, 6 and 7, we want to classify the angles as acute, right, obtuse, or straight. So MLN, starting at MLN, that was 60 degrees. That's going to be less than coautness, so it is an acute angle. Next we have is NLO, so NLO, okay, that's this small angle here from 60 to 90 is 30 degrees. You can also do 10, 20, 30, right? Less than 90 degrees, so it's also going to be a cute little angle. Very good. Number 12 wants to write two other names for angle 1. So 1 is labeled here, so we're talking about this angle going from X to the vertex Y to W. So we could either call it XYW or WYX. Just like with a segment or a line, the order in which we label them does not matter. It's only with rays that it matters because we always start with the endpoint. So you can call this angle XYW or angle WYX. And you can do number 2 on your own following the same pattern. Look at 14. So we got another protractor here. We want to find the measurement of angle ABG. So ABG. So that's going to be this green angle here. So starting at 0. Now notice this time 0 is on the inside. So if we were over here, we'd start with 0, which would be using the numbers on the outside. Okay, if we're measuring from the left, we're starting with 0, so we're going to measure with the angles on the inside. So it just depends on which side you're starting at. That's why the protractors, any good protractor is going to have the angles going from both directions. Okay, so we're going to start at 0, go up to 10 to 20, and that's going to be the long line here is 20. Then we need to count the singles here. So 21, 22, 23, 24. You can also see the other midline, which would be 25, and it's one less than that, so it is 24 degrees. Okay, the next thing we want to do, I don't think I made a duplicate, is we want to measure angle, the measurement. Again, the little script M, usually it's going to mean the measurement, just like the measurement of a segment. Now we're doing measurement of angle, EBA. So starting at E, going to the vertex B, and then over to A. So we're measuring the blue angle here. So the same thing, starting at 0, going all the way up, past 90, and it's going to be 100. And then we have to measure our ones, so 101, 102, 103. So 103 degrees. You should be able to do the rest of them. Number 20, we want to know if these statements are true or false on the back side. So 2 and 5 are adjacent angles. So angle 2 here and angle 5 over here. Are those adjacent? Well, what did adjacent remain? Remember, adjacent is next to, which means that it's sharing a common side or sharing a common ray with the other angle. Are 2 and 5, are they touching on the sides? No. 2 and 1 are touching, 1 and 5 are touching, but 2 and 5 are not. So that would be a false statement. What about 1 and 4? Are those vertical angles? Well, what are vertical angles? Those are congruent angles that are formed on the opposite side of an intersection of two lines. So they're across from each other. So if we look at 1 and 4, are those formed by the same two lines? This line and this line? Are they opposites? Yes, so they will be congruent. So whatever angle 1 is, angle 4 has to be the same thing, and 5 has to be the supplement of both of those, by the way. So they are going to be congruent. So that is a true statement. Name an angle or angles in the diagram that described by each of the following. So I'm going to ask you to give me the name of an angle that's complementary to angle BOC. Now what does complementary mean? Again, you can change the C to a 9, right? 90, so it's 90 degrees. So which angle forms 90 degrees with BOC? So BOC is going to be this red angle right here. So we have 90 on the other side, which means the other side of the angle here also has to be 90. So the complement of angle BOC is going to be angle BOA, or you could call it angle AOB. I think it's listed as either one on the answer bank. So either AOB or angle BOA. 32, this is the angle addition postulate. Just like what we did with the segment addition postulate, we can add up angles that are adjacent to each other. Just like with segment addition postulate, we can add up angles that that are all collinear and share a common point. We can do the same thing with angles. So we have angle AOB, which is color coded for you. It's going to be AOB is the blue angle. Angle BOC is the green angle. Okay, color coded makes this a lot easier. BOC. And then the red angle is angle AOC. AOC right there. Okay, so if you see these two, they are adjacent angles. They're right next to each other, meaning we can add up the blue angle plus the green angle, and that's going to be equal to the red angle, the whole thing, right? So when we're setting up our equation to solve for this one, we can say that 4x minus 1 plus 2x plus 15 is going to add up to be equal to 8x plus 8. So let me go ahead and move these up here and change over to my pen. I think that is the pen. Yeah, so we're going to add those together and set them equal to the whole thing. So the blue angle plus the green angle is equal to that one. So our first step here, we'll actually solve it out for you because you might need the help. This is just algebra at this point. Is combining your like terms, right? So 4x plus 2x is going to be equal to 6x. 15 minus 1 is going to be 14, so plus 14 is going to be equal to 8x plus 8. Next step, we want to subtract the 6x from both sides because we want to get all the x terms to one side. When we do that, it's going to go to 0, right? Those are additive inverses of each other. So we're going to be left with 14 is equal to 2x plus 8. Last step we have, or next to last step, subtracting 8 from both sides because we move all the constants to the other side. That's going to leave us with 6 is equal to 2x. Then we divide both sides by 2 because we don't want 2x, we just want x, which is equal to 3. So your answer is x is equal to 3. You'll do a similar process on number 32, except I think it uses these two angles instead. You can mark the angles in the diagram. You can go ahead and move the parts over there if you want. I think I actually had extras. Yeah, I did have extras. So you can do the blue angle plus the green angle is going to add up to the whole thing, however you want to do it. All right, solve for the values of the missing angles. Given that angle 1 is, what does that symbol mean? Do you remember that? So remember that symbol has two parts in it. The first part is the tilde. The other part is the equal sign. The tilde tells us that it has the same shape, and like a angle is the same shape as an angle, or a segment's the same as a segment. And then the equal sign tells us that it has the same size. So this symbol means that it's congruent, and it comes from two different parts, the same shape and the same size. So here we know that angle 1 and angle 2 are congruent, meaning they have the same measurement. So whatever this is equal to, so is the other one. So this problem can actually be a little challenging. You can pause the video and try to see how you would set it up, but if you're not sure, I'm going to do it for you because I know this is kind of a hard problem. Well, if both of these are the exact same value, I'm going to let that value be x. Now that I set them both to be equal to the same x, I can use that variable to be able to set up an equation to solve for it. Well, I also know that this has to be 90 degrees. So these three angles together are going to add up to 90. So I can set up an equation which will look something along the lines of this. All right, let me erase this. Or just delete it. That works too. And Command 2. So I'm going to set up an equation where I have x plus 20 plus another x is all going to add up to 90 degrees. Then I'm going to combine my like terms, leaving me with 2x plus 20 is equal to 90. And then when I subtract the 20, I'll get 2x is equal to 70, which will leave me with x is equal to 35. So that means that this angle is 35 degrees, and so is this angle. That keeps happening. I need to lift my pen better. All right, so if I add those together, 35 and 35 is going to be 70 plus another 20, sure enough, is equal to 90 degrees. And so we know we did it right. All right, one more. On this one, notice we have two 90-degree angles, which means they're going to be perpendicular. So if this is 57, all I need to do is find the complement of that. So 90 minus 57, which is going to be equal to 23. Okay, and then over here, we're going to do the same thing, 90 minus 61, which is going to be equal to 29. And those should be our answers. 33. Did I do that wrong? I believe so. Yeah, that would be 33. Sorry about that. Okay, we'll fix it. That's what I wrote. It was totally 33 the whole time. All right, so 33 and 29. So that's going to be the values for D and E. I think that's it. Nope, got one more for you. So this one might be kind of difficult to solve. You see M and N, of course, are going to add up to 90 degrees, but we would have to know what one of them is before we can find the complement of the other. So what other information do we have? I know there's a hint over here. Vertical angles are congruent, right? So if this angle over here is, let's say, 33 degrees, then we know the vertical angle on the other side also has to be 33 degrees. That's because they have the same supplement, which would be 147 degrees. And the supplement of 147 is, of course, 33. So if this is 33, we know the vertical angle immediately on the other side has to be 33 degrees. Then all we have to do is find its complement, because those two add up to 90. So 90 minus 33 is going to be equal to, let's see, 57 again. So N is equal to 57 degrees and M is equal to 33. And those will be two of your answers for that one. I think that is it. Yes, that is it. So just as always, you guys are doing really well. So thank you for working hard for me and watching the whole videos. I'm sorry this one went a little bit long. But yeah, so do the assignment. If you get stuck on anything, please let me know. You can just in Google Classroom in the private comments for the assignment. If you'll just tell me that what problems you would like to have the solutions for that you need help on, I will walk you through those problems when I type out the solutions for you. Okay, so I hope you guys have a good day, and I'll see you tomorrow. And tomorrow is Friday, so we only have one more day, and then you got the weekend, and it's a 3-day weekend because we have Labor Day, I believe. Yeah, Labor Day weekend is this weekend, which is really nice. So you guys will have time to get caught up. You also have time to relax, which will be good for all of us because, let's be honest, our sleep schedules are still out of whack. And also, if you're not caught up on your assignments, expect a phone call home. Yeah, so I'll probably start calling parents on Saturday. So make sure you're caught up on your assignments if you've fallen behind. Like I said in our little heart-to-heart on the last video at the beginning, if you skipped over that, you should watch it. Make sure that you're doing your assignments daily. Don't try to procrastinate and do them all at the very end of the week. Because that's not how we learn the best way. So make sure you're caught up, and if you did fall behind, we're going to start over fresh when we come back on Tuesday with a 4-day week, and let's try to get right back on track, because I don't want you guys to fall too far behind, and it makes it more difficult for me to help you if I have to keep going back and grade things that are even older. Eventually, it's just going to get lost. So hope you guys have a good day, and I'll see you tomorrow. It's almost Friday.